everyone. I am super excited to be doing our next. Well, thanks, Olivia, for the follow. Um, yeah, I'm super excited to be hosting our second quantum software talk. This is basically a space where we at the Unitary Fund, which supports a lot of open source quantum software, we find kind of different projects we find really interesting and cool and invite maintainers and developers to come chat about it so that you, the audience, can learn more about their projects and maybe find ways that you might be able to contribute to them. And thanks, ThonkPod, for the follow. Oh, wow, we're getting a lot of follows. That's great. So I want to introduce our kind of guest here today, really briefly. We've got Alex here. Oops, this side. Alex. And Alex McCaskey is a research scientist in the Computer Science and Mathematics Division at Oak Ridge National Labs. National Labs are really cool, by the way. He serves as the software lead for Quantum Computing Institute at ORNL, and is the project lead for XACC, the quantum framework, and QCOR, which is kind of what we'll be talking about today, the quantum classical C++ compiler. And like, honestly, folks, I've been super excited for this talk because I really like this project and I wanted to kind of like learn more about it, but this is kind of the great kind of kickoff point for me to get going on that. He received his master's in physics from Virginia Tech and bachelor's degrees in physics and math from University of Tennessee. That's cool. I did math and physics as well for undergrad. I could not decide which was cooler. Cool. Well, thank you again so much for joining us today, Alex. I am really excited to kind of both learn about your projects, what you work on, and yeah, I think I will just and I want to encourage the audience, like, this is very conversational, so please feel free to ask questions in chat. I'll be watching chat and will happily interrupt to make sure we answer, get the questions answered.
Compiler for heterogeneous quantum classical computing. Now, I can't see the Skype call here, so yes, if anybody has any questions, please just let Sarah know, and Sarah, just interrupt me. Otherwise, I won't be able to tell. But yeah, so I'd like to acknowledge my team here: Tien Nguyen, Daniel Cladino, Anthony Santana, Travis Humble, Eugene Dumitrescu, and Dmitry Liak are core developers, or working with the spec or the QCOR compiler itself. So I'd like to call them out and make sure to acknowledge them. For today's talk, QCOR. So QCOR is our quantum compiler. It is a language extension for C++, okay? So I'm going to talk about exactly what does that mean, how do we do it, what does a QCOR program look like, and then really dive into the technical details because, like Sarah said, this is an interesting opportunity. This seminar series is great for learning about these projects, but also possibly picking up people to contribute. So, and we're very interested in that. Everything here that you see is open source. So I'll dive into the technical details and then hope to give a little demonstration at the end if I have enough time. I'm going to talk at first about what do we think of quantum software, quantum computing from the DOE National Laboratories perspective, okay? And so we've got a number of projects or programs going on right now from the Department of Energy. The big two here that I'll talk about are this ARQC and QCAP project. These are really funding the development of holistic software architectures for quantum classical computing. And so I'll talk a little bit about that here at the beginning and give you an understanding of what are our software requirements for DOE mission relevant tasks with regards to quantum co-processing, okay? And so whenever you start off in any kind of software design process, you always say, all right, what are my software requirements? What are my use cases? Things like this. At Oak Ridge National Lab and a number of other national labs, we obviously have a heavy influence of classical heterogeneous computing with regards to a number of these like leadership computing facilities. Oak Ridge in particular perennially hosts or houses one of the fastest supercomputers in the world. Currently we have the Summit architecture, which is a classical heterogeneous compute architecture that's made up of like 4,000 classical compute nodes Each node has, I think, 6 GPUs available for offloading computationally intensive tasks for modeling and simulation activities that are pertinent for DOE. We had Titan before that. We're going to have Frontier soon, the first exascale machine. And so with that in mind, when it comes to software requirements for quantum computing here at the lab or at DOE, we want to borrow some of these kind of ubiquitous programming model ideas, or leverage research and development from past classical co-processing programming models as we move forward to think about what does it mean to enhance a Summit-like architecture with a QPU, right? In the future, as hardware improves, can we think about integration of QPUs with classical heterogeneous architectures as an accelerator, okay? And so we're interested in future CPU, QPU models, programming models. And one requirement that we think about is we need to make sure that what we do is at a system level programming approach. A lot of applications have been developed for these classical architectures. Most of them are in C++ and Fortran. We have a number of tools and compilers, parallel runtime libraries, all sorts of stuff that's kind of at this system level of programming. So this is one thing that we want to think about as we move forward. In the past, we've thought about at the DOE level this idea of test beds for quantum computing. There's a number of test beds out there. There's a number of projects that are interested in benchmarking and understanding applications and algorithms across a number of different QPU types. We want to make sure that whatever we develop is hardware agnostic. Okay, so that's requirement number 2. And then finally, we have a number of algorithm efforts that really require this idea of high-level domain-specific languages that are compiled or mapped to quantum hardware in a hardware-agnostic way. And so we want to be extensible for DSLs. We want to be language agnostic. We also want to ensure that what we provide on the software side for programming is a single source approach. Okay, and by that I mean that we pick up the efficiency of programmers leveraging languages in a single source context to offload computationally intensive work to a potential quantum coprocessor. And so, like I said, the big programs that are focused on this are DOE Oscar, the Advanced Research in Quantum Computing Project, and the Quantum Computing Application Teams, QCAT. So we've got a QCAT project funded at Oak Ridge with a number of other collaborating institutions. Our effort here was really focused, and this started about 2 years ago, this QCAT project for us. Our effort here is really focused on the development of a software stack for near-term quantum computation, and really thinking about it as a hierarchy of different thrusts, research thrusts. So talking about what does it mean to define applications at the high level, what does it mean to define control hardware libraries at the low level, and then everything in between, right? And so this is kind of where the QCOR project really grew out of, and we did some early prototype compiler development with Clang and LLVM as part of this work, and it's still going on. But really, a large focus of this work has been on near-term variational tasks and the development of a concrete specification for a programming language extension. So this idea of QCOR as an extension to C++, or now actually as an extension to Python, I'll show you that in a little bit. This really comes out of this QCAT effort where we really define what does it mean to extend an existing classical language for quantum computation. The next project that I'll highlight here that is directly funding QCOR development is this Advancing Integrated Development Environments for Quantum Computing, AID-QC. It comes out of the RQC program from DOE Oscar. And the idea here is to kind of collaborate with the QCATs and other DOE projects as well to develop a holistic software stack for the development of heterogeneous quantum classical computing for DOE mission relevant tasks. And this can be kind of focused on near-term applications, but also think about what it means to define a programming framework for fault-tolerant future tightly coupled models as well. And this project is decomposed into research thrusts as well for programming languages and compilers and validation and verification and other things as well. This is actually a point of collaboration with the Unitary Fund. We're collaborating with them and the team project for error mitigation strategies as part of this holistic software stack. And we are leveraging and building upon the QCOR infrastructure to provide a C++ single source programming model that serves as the foundation for high-level scientific libraries and then future language bindings to Python and Julia and et cetera. So think like the CUDA to NUMBA type of bindings, if you will. I'll talk about that a little bit more too. Okay, so that's kind of the background. Where did QCOR come from? These projects are really heavily invested in the development of this infrastructure, okay? So let's start simple. Let's talk about the anatomy of a QCOR program, okay? What is a QCOR program? First off, the first thing that we start with is this idea of a kernel of execution. And like I said, this borrows from this classical heterogeneous computing world where we think about, GPU kernels or CUDA kernels or things like this. For us, a kernel in QCOR is a unit of execution on the quantum coprocessor, okay? And we define it as a function, as a standard C or C++ function or a Python function. And note that everything that I'm showing you here, this is part of C++, the language itself now. If you leverage or use the QCOR compiler, everything you see here, you don't import anything, you don't include anything. This is part of the language now, okay? So here I'm showing a very simple GHZ state on n qubits, okay? You have access to all sorts of different quantum intrinsic instructions. So here I'm showing Hadamard CNOT measures, but you also have full access to C++ control flow, okay? So I'll show this in a sec too. Let's step through the individual pieces of this kernel, okay? So a kernel can be any C++-like function. It must return void. It must take at least one QReg instance as one of its arguments. The QReg is our abstraction of a quantum register, and we can allocate QRegs of different size. I'll show that in a sec too. It can take any number of function arguments. So you could think like I can pass all sorts of doubles or vectors of doubles or lists of whatever, all sorts of stuff so that I can provide a parameterized kernel for things like state preparation, for instance, right? All quantum kernels must be annotated with the QPU attribute, this underscore underscore QPU underscore underscore. And I'll talk about why that's important. This is our hook into some unique Clang plugins that we've developed as part of this project so that we're able to basically take these kernels and translate them into something that is valid C++ code. So everything you see here, if you ran GCC or Clang++ on this, it will not compile because this is a language extension that is not known by those compilers. QCOR provides this language extension and can parse these expressions, okay? The QPU attribute means I want this function to be compiled and executed on the coprocessor of my choice, okay, quantum coprocessor. And then the function body itself contains quantum code. It can be written in any available quantum DSL. This is where we're trying to get our extensibility with regards to languages. The most well-supported language that we have currently in QCOR is this XACC language, which I'm showing here, this XACC assembly language dialect. But also we have support for OpenCASM, and we have a very cool unitary matrix decomposition or circuit synthesis language that I also show that you can actually leverage within this function body to define quantum code, okay? And then, of course, we can leverage, like I said, all of C++ control flow, for statements, if statements for fast feedback, all sorts of stuff. Okay, so now just look at the entirety of a very simple QCOR program. We have this kernel. We've defined the kernel. It's a GHZ state on n qubits. So now to use it, all I have to do is invoke that function. It's just a function now, right? And so what do? I allocate some qubits to operate on. Here I'm saying give me 5 qubits. And then I run the GHZ prep state step and measure the qubits as part of that kernel, right? And then I can get reference to the results from that QReg. The QReg itself persists the results of execution. So I can get the counts out, for instance, and I can get other things that are pertinent for the execution, and then I can print them, right? So everything here is part of the language. I didn't include anything. I didn't import anything. This is part of the language itself. If you run the QCOR compiler, like I'm showing here, and specify a specific target backend with this QPU command line argument, here I'm targeting a specific IBM physical backend. I can specify the number of shots. I can do all sorts of just common compiler arguments like -O, so I can output this to a very specific, named executable, or I can pass new library paths to search and new libraries and new include header paths and all this kind of stuff. QCOR is a C++ compiler, essentially. And then, of course, the file itself. This gives me an executable, and I execute it, and this is running on IBM, so I go in the queue, and it comes out, once it gets through the queue, it runs and says it's complete. And you can see I've got the GHZ state essentially with a bunch of noise, right? So this is what you would see if you ran this compile command and executed the code. And one thing to note, here I've got a 5-qubit GHZ on the Boblingen backend. So this maps pretty naturally one-to-one on the connectivity of that backend. But QCOR does handle qubit placement automatically. And you can specify qubit placement strategies at the command line as well. And I'll show that in the demo, hopefully. Okay, so this idea of language extensibility, I showed you XASM in a GHZ state, but what about, can I incorporate OpenCASM? And we can do that because we are free to, we've defined this language extension. We have control over the function bodies themselves. So here I'm saying, I'm going to define a quantum kernel. It's going to take 3 QRegs. And I'm going to start off by saying, hey, use the OpenCASM dialect, okay? And here I've got OpenCASM code that's going to produce an adder, an adder of 3 plus 5 to produce 8, right? On the QRegC, essentially. And so we're leveraging a really cool library. I like this a lot, this stack library, STAQ. They have a really cool OpenCASM parser that we've incorporated as part of QCOR and XACC. And they extend OpenCASM actually with this Oracle syntax. So you can define oracles as Verilog, kind of hardware-like files. And the compiler will actually take that and decompose that into 1 and 2 qubit gates. So this is a really cool way of expressing an adder as a quantum kernel using OpenCASM. So we're using different languages here. And even more so on the bottom right here, you can switch languages within the kernel itself. So we actually analyze these step by step. And as you start off in the default XASM dialect, you can switch to OpenCASM, or you can switch to our unitary matrix decomposition language. It's really that easy. So another language kind of dialect that we've introduced, and since we have freedom to extend the language within these function bodies, we've actually defined a decompose syntax, okay? And the idea here is that programmers program at the unitary matrix level, right? So all quantum circuits ultimately are some unitary, operation on a, the initial qubit state. Here we're saying, let's create a controlled C0, but do it with its unitary matrix representation, okay? And so basically what you do is you open up this decomposed scope, you write down what your unitary matrix is, and this can be parameterized as well from the incoming quantum kernel arguments. And then you specify the QReg that you're running on, you close the scope and you specify the QReg that you're running on and the quantum circuit synthesis algorithm that you want to use. And so we have a number of these integrated within the platform. So here I'm using this QSearch algorithm from our collaborators at Berkeley to decompose that matrix into native 1 and 2 qubit gates for the hardware. And this is another example of mixing languages. I start by putting X gates down on all qubits. This is XASM, and I end by putting measures down on all qubits. This is also XASM. And we have a number of circuit synthesis strategies built in, KAK for 2 qubits, 1 qubit ZYZ rotations, QSearch, QFast is another one from our Berkeley collaborators. So this is really cool. And it gets even cooler in Python, actually. So in Python, to get this kind of decomposed syntax, we actually build upon this with expression as var syntax in Python. And what we say here is, if you want to express your quantum code as some unitary matrix, say with decompose on the QReg and then specify the synthesis strategy, specify as the matrix name, the variable name itself, and then you can put any Python code within this scope as long as you, at the end of the day, set U as a NumPy matrix. And so our compiler, QCOR, can pick this up and decompose that into 1 and 2 qubit gates. And I'll show that in the demo as well.
Quick question, Alex.
Yeah.
We got from chat, why is a QPU function returning void instead of the result of the quantum computation? So I think, yeah, like at the top where you're defining the controlled not.
Yeah, so that's a really good question. Honestly, there's no real definite reason why it has to be that way. This is really a design choice on our part. Specifically, it gives us a little bit more flexibility in parsing. So a really hard part here for the compiler is just parsing what's inside this function body. And if we have control over what comes in and what goes out, then it's a lot easier. And so if we say you can't send anything out via return, it makes it a little bit easier. And what we do instead is execution results are persisted to the incoming QReg, okay? And that gives us kind of a uniform interface for bringing stuff in and getting stuff out. So
cool.
I hope that answers your question.
We even got another one while you were talking about there. So can circuit synthesis optimization, qubit placement routines be specified using the command line arguments when compiling, or is that specified within the code itself?
That's another good question. For qubit placement, that can be specified at the command line or the Python command line too as well. And we actually can add API functions to specify this, at the programming level, but we haven't done so yet. With regards to the circuit synthesis work, currently you specify that in the code, but this is another thing that we could make to add an API call to change that or do it at the command line. We haven't done that yet, but that's really easy to do.
Sweet, yeah, great questions, everybody. Keep them coming.
Yeah. Okay, so now let's dive into the technical details. How do we make this work, and what are we providing, really? So QCOR is providing this language extension. It's enabling quantum language injection and utility within quantum kernels. It's hardware agnostic. We can target a number of different backends and simulators that scale on Summit-like architectures. We have so QCOR is a quantum classical compiler, right? So we have a full compiler pass infrastructure for quantum circuit optimization and qubit placement, like we've been talking about. Really cool. It's multi-model. So we're interested in these, obviously, in the near term, in these kind of remote REST API-based near-term algorithm execution models, right? But in the future, you'd hope to see tighter integration, local QPU, CPU node integration, and enable this kind of future local fast feedback type of functionality where you could measure a qubit, get its result, and then have that dictate what gates are executed afterwards, right? And so QCOR provides this. We provide extensible circuit synthesis, extensible variational algorithmic data structures. I'll talk about that too. And then this QCOR really provides a integration platform so that we can work with these third-party libraries in a multi-language way, so across C++ and Python. The component architecture looks like this. This is kind of how I see it in my head, very high level, like, how do these things interact? So QCOR sits here at the top. It's this C++ language extension where you define quantum codes within a quantum classical context. We've developed unique Clang plugins, specifically a plugin called the syntax handler, to handle quantum DSL or quantum language processing and transformation to valid XACC API calls. Okay, so this is kind of how QCOR leverages XACC. Through Clang, we produce valid XACC API calls, and we rewrite those kernels with that API. Okay, and in doing so, we get access to IBM and Rigetti and IonQ and Honeywell and all these different backends that we support, and simulators as well. And at the end of the day, you get an object file through compilation, or you get an executable and you just run it. So what is XACC? Let's kind of start at the ground up here. XACC is a system-level software infrastructure for quantum classical computing. Its goal is to provide a foundational infrastructure for tools and compilers. I like to decompose its architecture, as you see here, in this sort of compiler textbook, 3 layers, where we map any number of languages or dialects of Chasm or what have you into a core, middle end, intermediate representation that's amenable for optimization and transformation. And then we have a back-end infrastructure for injecting quantum processors and simulators, which take as input the processed IR, map to native assembly for the back-end, and execute, returning the results to this QREG instance. Okay. Everything you see here, this is a service-oriented, I like to call it a service-oriented architecture. Okay, so the layers that you see here are made up of core interfaces that we extend for concrete workflow items. Okay, so we have an interface for compiling languages to the IR. The IR itself is made up of interfaces that we extend for Hadamard's and CNOTs and all these different instructions, right? Our back-end infrastructure is made up of services, interfaces, pure virtual classes that we implement for the given backends that we want to target, right? And we do this through this library called CPP microservices. Essentially, everything is a plugin that's dropped into a folder. Your XACC install may not be the same as somebody else's, dependent on what plugins you've built and injected into your system. You have complete control over your quantum classical workflow in this way. I like this picture because it gives you an idea of the breadth of what the XACC workflow provides via this extensibility. We have extensions for, like I said, compilers and algorithms and observables, operators, classical function optimizers, all at this kind of programming level. At the compiling level, we can do we can express these circuits as our core intermediate representation. We can generate that IR via synthesis strategies. We can even work at the pulse level within this IR as well and target things like open pulse on the IBM side. We have transformations on the IR. We have a lowering workflow section that will actually take the IR and map it to native 1 and 2 qubit gates for the hardware, or schedule pulses in the open pulse case. And then, of course, execution on the back end. And then a key one here is we also automate and provide an extension point for error mitigation. Okay, I'll talk about that in a sec too. Here's what it looks like for a full like XACC quantum simulation code, right? And notice there's no single source flare here. This is not, so QCOR basically elevates this to the language of C++, right? Here we just have API calls, right? So we get accelerators, we get optimizers, we get compilers and compile source strings, quantum source strings to IR. We get algorithms like VQE and we execute them. What QCOR will do is essentially elevate this to the level of the language itself, okay? All right, so let's dive into QCOR. So I think of the actors on the QCOR system in two different ways. So you have your typical user and you have your developer. Both will leverage the QCOR compiler. QCOR is decomposed into compiler and runtime packages. So the typical user will basically interact at the compiler level, provide source files that they compile for given backend architectures. The developer may actually tweak the runtime, right? So we have a number of different extension points within the runtime for variational tasks or expressing quantum kernels in memory, like as an object model, but also a key quantum runtime backend hardware abstraction layer that developers may work at this level, and a number of other things that I'll dive into in the next few slides. But this is how we decompose QCOR, the package itself, right? So a QCOR compiler, a Clang++ driver that's going to drive this kind of like syntax handling, mapping quantum code to valid API calls with XACC, and then the internal runtime, which it'll leverage to do all that stuff. So this is really cool work. So how do we take these function bodies, which are written in invalid C++ code, right? So like I said, GCC and Clang++ will throw an error if you just pass, one of these QCOR programs to it. How do we process that to something that's valid, that the compiler actually can compile? And what we've done as part of the AQC work is develop a new plugin interface to Clang. So Clang has a number of plugins that you can kind of inject for analysis and things on the abstract syntax tree and all this kind of stuff. We've made a new one and we called it the syntax handler. Okay, this is actually work done by my colleague Hal Finkel at Argonne, or now at DOE. The syntax handler maps invalid function bodies to valid ones. Okay, so a DSL to valid C++ API calls. A very easy example for this is given a function foo down here, right? I've got some code in here that's just a sentence, okay? And I want to make a syntax handler called tokens that maps this function body, or basically wraps it with a printf. So it's now valid and it will print that sentence, right? So what we do is we implement the syntax handler interface, which exposes a get replacement method. It will take the Clang preprocessor, but critically, it'll take the tokens that make up that function body. So when you compile a C++ code, basically what you're doing is you're lexing that source string into a series of tokens, and those tokens are what is used to build up the abstract syntax tree, right, internally. So we get an opportunity to look at those tokens, analyze them, and then write a new code to this raw string O stream, this output stream, okay? And so what this specific syntax handler will do is it'll take those tokens, it'll loop over them, it'll write this static const char tokens equal thing to a variable, and then it'll wrap it with printf, right? And so now when you compile with this syntax handler, this is valid, and it will compile and it will print the sentence that's within that function body. So in QCOR, we build on top of this, right? So we have a QCOR syntax handler. But in order to get this kind of language agnostic, language extensibility, we extend that further with regards to another extensible interface called token collector. And we implement the token collector for all the different languages that we're interested in. So we have an XASM token collector, we have a Pi XASM token collector, we have an OpenCASM token collector, and a unitary matrix token collector, okay? And so now our QPU attribute that we talked about earlier is actually just this Clang syntax parlance, this jargon here, right? What the syntax handler name is QCOR, okay? So there's a lot here to talk about. I'll just kind of keep it at a high level. We can switch token collectors within the code by saying using QCOR language name, so using QCOR OpenChasm, which you saw earlier, okay? And the goal of these token collectors is to take the invalid quantum DSL in the function body and map it to valid C++ code. Specifically, what we do is we keep the function that you had, so the function signature still remains here. We forward declare a new function, okay, and we call that function, okay? It's the same argument structure. We then take the name of that function and create a new subtype of a class within the QCOR runtime, this quantum kernel class, and it gives us all sorts of functionality that I'll talk about in a second. And we implement its destructor to perform the construction of that code via the XACC IR and execute on the XACC backend, okay? And then that forward declared function that we talked about at the beginning is then implemented to just instantiate a temporary instance of that class and then exit. And that will kick off the destructor and kick off execution of that function, okay? So there's a lot here, and there's a lot more in the paper that I'll reference at the end that will go into the details. But so basically the idea here is we have this new quantum kernel subtype. We implement the destructor to execute on the back end. What do we put here? We hook up to this quantum runtime piece of the runtime package within QCOR, okay? And this delegates to XACC directly. So what is the quantum runtime? Quantum runtime is another extension point within the framework, okay? And it basically enumerates all the different 1 and 2 qubit gates that we might be interested in and gives us a way to kind of extend that further as well. But this is where we extend it for the two models that we're interested in, for this near-term quantum execution model, or there are these remotely hosted processors, or this future fault-tolerant, tightly integrated model, right? And so we call this NISQ and FTQC within the platform, okay? And these guys both target XACC accelerators, so IBM, D-Wave, you know, well, not for the gate model, not D-Wave, but IBM and Rigetti and others and the simulators. Or on the FTQC implementation side, it will target our simulators that are built with support for single instruction execution in sequence, as well as if statements and conditionals and measures that give back results, okay? The quantum kernel, just to quickly touch on what that type itself is that we subclass as part of the Clang syntax handling workflow. This basically models a quantum kernel function. It's constructed with the incoming quantum kernel function arguments. The really cool thing I want to highlight here is that the quantum kernel as a class gives us an opportunity to define relevant or pertinent methods, static methods, that give us related circuits. So for instance, I have some ansatz here. Within another quantum kernel, I can actually leverage its control version on a single bit, right? Or I can get its adjoint or reverse, or I can print it, or I can map it to OpenChasm, or map it to a unitary matrix. All sorts of things just by providing static methods on this quantum kernel class. And then, of course, I said that QCOR is an optimizing compiler and performs qubit placement. We have a pass manager for this. This is a very familiar pattern. This is an LLVM. Qiskit has a similar infrastructure as well. Our passes are XACC IR transformations, which are an extension point in the platform. So we can implement this for a number of different strategies and integrate third-party libraries to do this work for us as well. So we have implementations from the Stack library. We have XACC ones. We can integrate Qiskit passes. We have some work from the University of Maryland, the VOQC, optimizing compiler work integrated within QCOR. And we basically expose an opt command line argument. So we can specify the opt level. So opt level 1 will get a certain number of passes that will operate on the circuit at runtime. Opt level 2 will do an extra set of optimization passes. But also we integrate as an XACC IR transformation placement strategies as well. And there's a number of them implemented. Some of them are noise adaptive. Some of them are trying to seek out shortest paths for swap gate insertion and all this kind of stuff. And we benchmarked this, and here's some results. But basically, the idea is that this happens at runtime, okay? The quantum kernel is optimized, and the placement occurs at runtime when the kernel is executed.
So that's probably Odi Mateo was asking about circuit optimization and stuff before, so this would probably be a great place to, like, if you had a specific strategy you wanted to try, to add it
Yeah.
in. Cool.
Yeah,
I love
exactly. So
this.
you just implement a new IR transformation, and we're actually building up a very robust documentation site that's going to detail how to make these plugin extensions across the framework. So there will be a good examples there for how to do that.
Docs are always good.
Yeah, they're great. Not as fun, but they're great. Anyway, okay, so now let's go into automated error mitigation. So XACC provides this accelerator interface for injecting backends. We actually, if anybody's familiar with like the Gang of Four object-oriented patterns book, design patterns book, we actually build on top of the accelerator a decorator pattern. We call it the accelerator decorator, which basically means that the decorator is a subclass of accelerator, but it contains a concrete accelerator, okay? And its execution implementation will execute on the decorated accelerator, but introduce an opportunity for pre and post processing, which is very good for error mitigation strategies. So we implemented this with the Matik library, implemented a Matik decorator whose execute will, leverage Matik to execute on the desired backend, but then do the zero noise extrapolation to produce higher fidelity results. Here's an example of how to use it. I have a noisy zero kernel where I'm just putting X's down 100 times and measuring the 1 qubit. I should expect to see 1 essentially for its expectation value. QCOR, we can also specify noisy backends. So here I'm saying, give me the error simulator with this noise profile, and compile this and execute it. And I see I got a noisy expectation here, 0.89. And do it again, but do it with this EM flag and specify that I want to use Matik for the error mitigation. And I can see that the zero noise extrapolation shifts it closer to 1, which is what we expect. So that's really good. All right, so let's go into the variational data structures really quickly. So we start off with an operator. The operator exposes an interface for general algebra. So we implement this interface for Pauli operators and fermion operators, and even more complicated chemistry operators. So we have a create operator API call where we can create Pauli operators or fermion operators from string. We have a really convenient, X, Y, Z API for building these up kind of more programmatically. We have fermionic functions as well. So A dagger A. We can create transformations on the operator. So here's a Jordan Bigner transformation, for instance. And then this like chemistry operator, we have PySCF, we have Psi4, we have a number of these implemented where you can provide an options list essentially and specify like a basis set and a geometry, and you'll get like the H2 Hamiltonian here in this case, right? So that's really cool. We have this concept of an objective function for these variational algorithms. So the idea here is a functor-like data structure that's extensible, that models y, a scalar, equal f of x, where x is a list of floats or doubles, right? So this is kind of ubiquitous across these variational tasks. Subtypes define pre-processing, execution, and post-processing workflows. We implement this for VQE and some machine learning algorithms and others. The objective function, basically you say create an objective function, you give it an ansatz and an operator. So in this case, the default is VQE, and we're going to basically produce, the expectation value of this operator, the energy in this case, at the given optimal parameters. We're going to try to optimize this or even loop over it if we wanted to for concrete parameters. We can execute the objective function and all sorts of cool stuff. Optimizers are really key in QCOR, and this is a key thing coming out of the QCAT work. So we can create optimizers. We have an optimizer interface. The goal of an optimizer is to optimize objective functions or general functors of a specific argument type or structure. And we've implemented backends for this for MLPack and NLOpt and scikit-quant, which is a library coming out of our collaboration with Berkeley. CMAES, all sorts of different strategies can go behind this interface, and this optimizer can be passed to all these different algorithms as input, right? So we can, run VQE algorithms with different optimizers, different derivative-free optimizers, or different gradient optimizers, or what have you. All right, so now so this is about C++ and extending C++, but now we've got some really cool work extending Python. So the idea is to do the same thing that we've done in C++, but do it for Python and do it via just-in-time compilation, JIT. So the idea of just-in-time compilation is you basically compile and execute your code at runtime in some other code. This is supported in LLVM. LLVM has a just-in-time engine. It takes as input an LLVM IR module and outputs a function pointer that you can now execute, which is really cool. And this is kind of how a lot of GPU or some GPU programming models are accomplished in Python, Numba being a very popular one. The pros here are the flexibility for just-in-time compilation. It's useful for language extensions, and the cons may be performance, right? Because now you're doing a compile workflow at runtime. But we overcome this with caching of the compile results. And let's go into the details of this, right? So now in QCOR, we have a QJIT class. And this actually is a very powerful data structure, okay? So the idea here is that we have just-in-time compilation for quantum kernels. So everything I've shown you here is ahead of time compilation, right? You define your quantum kernel, it's static. It has some input arguments, but overall it's static at compile time, right? Instead, let's define a QJIT class and be able to pass kernel source strings to it to just-in-time compile at runtime, which then gives us an opportunity to extract a function pointer that we can now execute, right? So bell functor here was just-in-time compiled, and I can now execute it, right? The idea here is that we're integrating the QCOR syntax handler, mapping invalid C++ code to valid C++ code. We're leveraging programmatically Clang's code gen infrastructure. So we're actually mapping that to an LLVM IR module. And then we're going to use the LLVM just-in-time compilation infrastructure to take that module and output a function pointer. And we cache the results. So you'll see that this workflow is slow the first time you do it, but every other time it's going to be really fast because we're using the cache results. So we use this to extend Python, okay? And so instead of the __QPU attribute in C++, we define a QJIT Python decorator. This Python decorator delegates to the QJIT infrastructure that I just talked about, okay? And so the idea now is that you have this Pythonic XACC dialect within your Python function. So def bell here is a Python function. Within it, the function body is not interpretable by Python, but we leverage the Python inspect module within this QJIT decorator to extract that function body as a string and then give it to the QJIT infrastructure in C++ to produce a function pointer that we execute under the hood. But at the Python level, you just see a function, and it's just a Python function. You allocate some qubits and you execute it, and you print the results, right? So that's really cool. The QJIT data structure itself is really interesting. It basically delegates to the QJIT C++ infrastructure. Like I said, source to Clang, to LLVM, to function pointers, and stores them internally. And it exposes an API for the control version of certain quantum kernels, or printing the kernels, or even mapping the kernel to OpenQASM so you can integrate with Qiskit, all sorts of really cool things. So finally, just to end here, we see QCOR as an integration platform, and this is because XACC is its foundation, and it's this service-oriented approach to quantum classical computing. It's really easy to integrate state-of-the-art tools, techniques, and frameworks. So let me give you three examples, really. So the first one that I'd like to show is in this new Pythonic just-in-time language extension. It's really easy to go from QCOR to Qiskit, right? So if I want to define a quantum kernel with QCOR, I can take that kernel, this GHZ state, for instance, GHZN, and I have methods on it because it actually is part of this QJIT decorator. So I can say, hey, take this kernel and map it to OpenQASM. Okay, now I have an OpenQASM string, and all I have to do is say quantum circuit from QASM string, and I have a quantum circuit in Qiskit, and I can go on with the rest of the Qiskit infrastructure, right? So that's really cool. The other thing, we have tight integration with OpenFermion now within this Python language extension. So I've shown you our QCOR operators, but you really should be able to provide OpenFermion operators as well. And we should be able to map between the two and let you seamlessly use both, right? So here I've got the VQE problem for 2-qubit deuteron. I'm defining the Hamiltonian at the fermionic level with OpenFermion. I said import fermion as FOP. And then I use the rest of the QCOR API, create objective function, give it an operator, and give it the OpenFermion operator. And under the hood, we'll map that correctly to the internal C++ data structures that we need, create the optimizer, optimize, seamless interaction across these different libraries, which is really cool. Okay, so and then the last thing here, I wanted to highlight what we're doing with Q Sharp. So this is very early prototype work. Everybody's, I think, familiar with Microsoft put out a QIR, a quantum intermediate representation specification over the last few months or something like this. So the idea here is we're in the C++ world with QCOR. We have direct access to great tooling from LLVM and things like this to interact with the LLVM intermediate representation. So the key point here is, can we let users program with Q Sharp, compile to QIR with Q Sharp with a Q Sharp compiler, and then link with QCOR to enable backend execution on any XACC backend. And we're talking, any of the physical backends or the summit level simulators, anything. And so we've been able to kind of demonstrate this prototype. This is actually part of work that's going to be ongoing this entire year. Take a very simple Bell state in Q Sharp, compile it to QIR. What you get is a LL file, which is basically this human readable representation of the LLVMIR, this disassembled form of the LLVMIR. And then I'm showing you a shell script here that would basically take that and link it with our implementation of the Microsoft QIR functions, right? So basically the bell.ll contains these kind of opaque functions that are to be implemented for whatever backend you want to target. So it's really flexible. The QIR is a really great effort. I'm really excited about it. But anyway, so basically you say, all right, I had this LL file. Let me map it to a bitcode file with LLVMAS. Let me link it with our Microsoft QIR adapter, which is going to delegate to the delegate to the quantum runtime class that I talked about earlier. And then let me lower that the result of that linkage to object code, and then compile with QCOR so that I can link with all the QCOR libraries and the XACC libraries and create an executable that I execute. So now I have a pipeline that will take me from Q Sharp to an executable that will run on XACC backends. All right, so let's talk about a little demonstration here. So let me switch out of here. And if anybody's got any questions, now might be a good time while I switch. All right, so installation is really simple. We have a new website, docs.aqc.org. This is coming out of the AQC project, okay? And so this is the homepage. If you scroll down, we got a little bit of info here and some examples, but if you go to getting started, installation is now a single command, and this will work across most Linux operating systems or distros, and Mac, Mojave, and Catalina. So basically all you need to do is copy this command, this install command. I have a empty Ubuntu Docker container that I've started up before this started. So just copy this here, and this will start to download our binary packages, right? So this is actually built nightly. These are Debian packages. This is Ubuntu, so it's going to leverage apt-get. We also have homebrew bottles, so this will work on other Linux distros and Mac OS. This will take a couple minutes, so I'll go ahead and switch over, but we'll come back in a little bit and check it out. But other than that, I'll just move on to the rest of the demonstration.
Is there a nice like pre-built Docker? Is that what you're saying? Is there a pre-built Docker image that I can just get find on Docker Hub or something like that?
Yeah, so this is me just I just wanted an empty OS, and so I just kind of made this Docker image to show you guys how it will install. But we do have Docker images as well. So you can actually use, if you go to the, I believe the README for QCOR, and we might have updated it recently to remove it, but we do have a QCOR/QCOR Docker image that will actually serve up a Eclipse Theia IDE into your web browser with QCOR already configured, able to use, already built and ready to go. So we have both. Okay, so let's start off with a phase estimation example, because this really shows kind of the power of quantum kernels and these static members that I was talking about. So basically what I want to do is, we know quantum phase estimation, you have some oracle on some state, you're trying to figure out the phase here, right? And so, hey, let's define the oracle as a quantum kernel, right? We just annotated QPU. For this case, I want to do a T gate on the one state to basically figure out that the phase coming out should be, I think, 8, because there's a 2 pi here somewhere. But so we just define
I always miss the factors of 2 pi.
Yeah,
with phase estimation, it's that, or it's 2 times that, or it's half that.
It's either one, half or 2. That's how physicists talk, right? Like there's a 2 in there somewhere, right? Mm-hmm. Anyway, so yeah, the oracle itself is just a quantum kernel. It takes a QReg, and here we're going to put a T gate on the last qubit, right? So that's our oracle, okay? The phase estimation algorithm itself can be written as a quantum kernel as well. It takes a QReg. We're going to work on 4 qubits, 3 counting qubits for this case. You know, we can do any classical code here, right? So I can allocate variables like n qubits is q.size, right? The bit precision should be 3, should be 4 qubits minus 1, right? Start off by allocating or operating an X gate on the third qubit. Apply my Hadamard's, and we have really cool Pythonic C++ functions to kind of make this translation really simple between the Python world and the C++ world. You know, allocate or put a Hadamard on all qubits. And then here's the really cool part. This is the application of that controlled oracle, the iterative controlled oracle, right? And since oracle is a quantum kernel and quantum kernel exposes a controlled version of it, we just use that, right? So we say control on the ith bit and give it the argument structure that we need for that kernel. So this is the Q, right? The QReg, essentially. The other cool thing.
Quick question. So we got from Esther. It looks like so QCOR would then translate between QAR instructions and the specific backend instructions available in XACC.
XACC, yeah. Yeah, so that's exactly right. So basically what's going to happen here is under the hood, we're generating an instance of the XACC IR. And that IR will be passed to the backend. And the backend is tasked with mapping that IR instance to whatever it has to send to the backend, right? So it'll map to its native gate set. So for IBM, U3s, and CX, right? And then it will submit that via a REST call, okay? The other cool thing here is that, you know, we can build libraries for QCOR, right? So we have internal libraries like we always say QCOR underscore whatever it is. So this one's the quantum Fourier transform library. And I just have to include it and I get all these quantum kernels, right? So if I want to use the IQFT, the inverse quantum Fourier transform, I just include that because it's another library essentially, right? So I'm going to apply the IQFT and then I'm going to add measures to the end so that I can see what the result was. Main is just as you've seen before, allocate 4 qubits, run the quantum phase estimation algorithm, get the counts, print the counts essentially so we can see it. We should expect to see a 100 bit string only, 10,000. We're going to do like shots for 1024, right? So QCOR, that's QPU, and we're going to target a simulator first. So we have a QPP simulator, shots 1024, and then phase estimation. Okay.
It's a little bit off on the right side, but that's okay.
Oh, it did go off on the right side? Does this help?
Well, yeah, close enough.
There we go. I'll just do it like this.
Yeah, that's fair.
So now I compiled this. I have an a.out. I'll just run it, right? So now I see the bit strings. It came back correct. That's great. For the demo, there's other things we can do, right? So if I want to see what the kernel looks like, I can say something like quantum phase estimation, print kernel, give it an output stream, cout, and then give it the arguments, okay? So then I just hop over here and compile it again. This will compile, and then I'll run a.out again, right? And we'll just see what the results were.
Okay, and say,
print like, the chasm here. Yeah.
Oh, nice. Yeah, no, like, so usually I'm not the biggest fan of C++. I understand it's generally the right choice for things, but I very much like Python, and seeing kind of the notation and kind of how you've borrowed from some of the like more Pythonic things definitely makes this feel a lot more accessible. Yeah. I love it.
Well, the really cool thing is now with the Python API and these little cool, like, you know, syntactic sugar things here, right? Mm-hmm. Like the code looks exactly the same in Python and C++. So here what I'm doing is I'm going to compile for a noisy backend. I'm just going to use the air simulator. They have great noise simulation capabilities. And boom, I get a noisy result, right? So I see what I should see, which in this case, it's not the same as before because air uses I believe, MSB bit encoding versus LSB bit encoding for the QPP simulator. But you see a noisy result, which is great, okay? So that's the phase estimation example. Let's hop over to GHZ placement. So I want to show you how we can actually automate the placement algorithms here. So here I've got the GHZ state. It has a connectivity that's like 0, 1, 1, 2, you know, on and on and on. We're going to do it on 6 qubits for the Böblingen connectivity, which half of it I'm showing here. And we can just kind of print and see what happened for placement, right? So QCOR, QPU, IBM, IBM-Q, Böblingen, shots, 1024. I don't even think we need that, but we'll just do it anyways. GHZ placement. Okay, so this is going to compile. It's going to give me another a.out. I could also specify the executable name with just a -o, but it's just easier to say a.out. Okay, so this will run. It's going to print the chasm, but it's going to print it in a place like what it would look like on that connectivity, right? So you can obviously see the swaps inserted here, okay? So we have 6 qubits. We can't just put them all here. And so there's like a swap that goes in, I think, around here or something like this, right? So that's really cool. We can also execute this on the back end. And I'm pretty sure that the bubbling and back end didn't have anybody on it when I left before the talk. So let's just see what happens. If it's going to take a while, I'll just keep moving on. But so this will execute on the IBM physical backend. This is really cool. 1024 shots. So there's the placement result from print kernel. This is running. It's in the queue. And it looks like there's some other people in the queue. So I'm not sure if we're going to sit here and wait for it. We'll come back to it. Yeah, fingers crossed. But earlier it went in like 2 seconds. It was really cool. I love it when that happens. All right, so let's imagine that you have some OpenChasm code, right? We should be able to integrate OpenChasm code as these files because a lot of people use these for benchmarks, right? Mm-hmm. So I'm going to use this for to demonstrate optimization, okay? So if you want to just include an OpenChasm code, you can do that because this is C++ and we have the preprocessor, okay? So here I have a quantum kernel. I say I'm using OpenChasm. I include the file itself just like I would any other header file. The preprocessor will actually expand this into the function body, which is really cool. And I'm going to run QCOR with opt level 1 and print the opt stats. Okay, so QCOR opt1, print opt stats, and then run the code. Okay, so this is compiling and it's building into the executable this just-in-time at runtime optimization workflow. Okay, so this ran and it prints out detailed stats about what happened. So we have a number of optimization strategies built into opt level 1. So rotation folding went first at 480 gates before and 399 after. The next one took it from 399 to 285 and then 285 to 284. The last one didn't do much, but so this kind of shows you, what you can do with the optimization workflow within QCOR.
Seriously, and then the last thing that is so cool. Like having spent a lot of time trying to figure out how to implement these in, well, in this case it was in Q#, but like this is so nice. Like, and I love the little printouts showing you like how much progress you made each one. Well, we've got a great team and they've been doing a lot of great work. So I've got 2 more examples. Is it okay if we go a little over? Oh yeah, let's go. Okay, cool. All right, so let's say, we had this paper. Let me see if I can zoom out here and if you guys can see it. We had this paper a few years ago. I like this paper. I mean, I like this work because it was a lot of fun, but this is a great hello world for VQE. So you'll see this in a lot of our examples. This is the Deuteron problem, right? And I hate that this little thing is over here. Let's see if I can get rid of that. There we go. Okay. So if I scroll down, oftentimes you read these papers and you're like, okay, they've expressed maybe the state preparation circuit, as a, exponential, right? Like you would in the paper, right? It'd be really cool to be able to just kind of code that up, right? Instead of, hand figuring out like what the 1 and 2 qubit gate sequence should be and the, where the parameterized, RZ should go and all this kind of stuff. What if we could just write it as it is, right? And so that's what we're going to do. So this is the 2 qubit unitary for the Deuteron problem, e to the I theta over 2, and then this kind of poly operator. So let's hop over there. We're going to do this in Python, okay? And this is that cool decompose syntax I was talking about earlier. So we start off, we just import QCOR, and import it all really, so we don't have to keep saying QCOR dot. We write a quantum kernel, we call it onsats. It takes a QReg and a list of floats. You could also just take in a single float because this only has 1 parameter. We annotate it QJIT. We operate an X gate on the first qubit because that's what the paper told us to do. We now use this with decompose syntax, and the unitary matrix variable name is just U, okay? We are now free to put anything in here that will build up that U, which is really cool. So what I'm going to do, the easiest way, is to use SciPy sparse, XM, and OpenFermion makes it really easy to use qubit operators and get sparse operator versions of it, right? Which is really nice for SciPy sparse versions of it. So this is our onsats. The U itself is e to the, it's just the same thing as you saw in the paper, except we have to put 2 dents here at the end because we want to map it to a NumPy matrix. We define our Hamiltonian, which is in the paper as well. This is literally like pen and paper. This is exactly what it looks like in the paper itself. We create the objective function. This is the VQE objective function. We say we want to do gradient-based optimization. We give it a gradient strategy.
We get NL-opt, and we specify LBFGS because that's the gradient strategy, the gradient optimization strategy we want to use. We optimize, get the results, print the results, and let's see how that looks. So let me move this over so you can see it. So this is just in Python, the Python API. So we'll just say VQE. And you can also, with the Python API, put a QPU as well. The default is QPP, so that's all I really care about. So I'll just let it run. So this is just in time compiling that kernel and running that Python code at runtime to generate that matrix data. And then we're going to load that into our circuit synthesis strategy, which I forgot to mention. We could specify that. This is a 2-qubit problem, so I'm going to use KAK, which is a very popular one. I could use QSearch or QFast or whatever. And this ran, right? So it went through the full optimization loop. This is the exact energy that's in the paper. I did good. This code worked. And here are the results, right? So this is really cool. This is a really cool way. I mean, we have to think about how do we make this scale, to larger and larger unitaries, but, at some level we can't. But for some of these kind of near-term problems, this is really interesting. I can also print the kernel, right? So let me go ahead and turn that on. So this is a quantum kernel, so I have all these static members on it. And I'm going to print the kernel at the optimal results. So basically what's coming back here is the optimal value as a tuple and the optimal results, okay? So you saw that here, it's a tuple. And so then I print the chasm, and it looks cool, like, this looks like it worked, okay? The last thing I wanted to show is the FTQC mode. So here, this is another Bell state, but instead of this kind of like remote NISC mode where I'm going to submit a chasm and let it run 10,000 times or whatever and get the counts back, I'm going to execute these quantum instructions in sequence and get measurement results to dictate what else I should do. So put them in if statements, essentially, right? So here I've got a Bell state kernel that will take a QReg and a number of shots, okay? And I'm going to loop over those shots and just run the code. So Hadamard, C0, that's the usual, right? Measure, get the results. Ideally, these should be the same, right, for the Bell state. And if it's noisy, then it won't be. And then at the end, I reset the state back based on the result. Allocate the 2 qubits, run Bell. So let's do this real quick. This is C++, so I got to run the QCOR compiler, QPP, and for FTQC, you have to specify the quantum runtime, FTQC, okay? And then I give it the C++ file. This will compile. I'll get an A.out, and I will run it. And you'll see, for a perfect simulation, you should only ever see that they matched, right? This is what printed for 50 times or however many times I did it, right? So now let me go ahead and do, and this is using conditional statements. This is really cool, right? I mean, like, we're not ready for this for physical hardware, but this is like, hopefully in the future we can leverage this. So IBM Q Vigo, I think. Let's see that. This will run on air with a noise model that's from the IBM Q Vigo backend.
Yeah, I was going to ask why this example necessitated the FTQC, but that makes sense. Like you're conditioning on classical logic. It's truly a hybrid sort of program.
Exactly. Yeah. So I'm making measurements. I'm getting a 1 or a 0, and I'm doing things based on that 1 and 0. And specifically, I'm going to reset the qubit if it was a 1, right? And so here you see for a noisy backend, I got some times where they didn't match, and that's to be expected, right? Okay, so that's pretty much the big demo I wanted to show. Let me show the final slide here real quick. I want to thank everybody for your time. I know I went a little over 1 o'clock, but I came in at just an hour as I timed myself, so that's really good. Oak Ridge is focused on the development of frameworks and retargetable compilers for near-term and future fault-tolerant heterogeneous quantum classical computing. Documentation page, please check this out. If you find any bugs, there's a link there for filing bugs with our issue tracker. Here's the mirrors for the XACC and QCOR repos under the AQC banner. Recent papers, here's my email. And I'd like to thank DOE, specifically Quantum Testbed Pathfinder, ARQC, and QCAP programs for the acknowledgement. And thank you guys for your time.
Well, thank you again. Here, I'm going to, don't worry, everybody. I'm going to get all of these links, and I will post them on the Discord. And when we upload the video, I'll also put them in the description, so you can make it easy to click on and go to these links. You want to turn your camera back on, Alex?
Yeah, I can do that.
Cool.
I didn't know when I should, so.
No, that's okay. That's okay.
So here, And here, I'll stop sharing.
We're doing this through Skype in the browser, and apparently that can only
Yeah.
conceptualize one video stream at once. So, but yeah, no, this is so awesome. Like, and I really want to highlight some of the things, like, at least that I personally really like about this project. Like, um, you know, as I said before, like I'm kind of generally a Python developer. I also really like Q Sharp, so I love that it actually there's so much integration between these tools because we aren't really at a point right now where lock into a specific platform really makes any sense. So having a tool like this where you can basically choose your front end, choose your back end, and really have it super easy, literally just like command line arguments to change where you want it to go. Like, and also thinking through like the magnitude of how you how to make sure all of that glue works is definitely not a trivial project. So definitely props to you and your team. Like this is a really really cool project.
Yeah, well, thank you. We have, I mean, this is like a cross institution thing. There's, a
Mm-hmm.
lot of things going on, and we've got a lot of great people working on it. The idea behind the AQC project, honestly, and then also QCAT is, there's a lot of great effort, a lot of great research and development going on in the quantum software community and in the open source quantum software community. And, we don't want to like leave anything out, right? Like, we want to be able to leverage all the wealth of development coming out of the community. And so that's been kind of a mandate on AQC is to develop a holistic quantum software stack, but do so in a way that leverages or can bring in these other libraries as well. So I think we're kind of tracking toward that, which is really cool.
So I have, if anybody in chat has questions, please feel free to put them in now. Um, I will ask one other quick question while I'm waiting. If someone was interested, say they watch this talk, they're super excited about the project. What would you kind of see? Like, is there kind of like an area where it's a good place to start looking at contributing? Like, is there like a do you want to put a bounty on something where you're like, I really wish we had X and we just don't have time to do it right now?
Yeah, I mean, we could. How much time do you guys want to stay here?
Well, other quick question: do you tag good first issues on the repo?
Yeah, we usually do. Yeah,
Cool, cool. So
especially
that's
the
always a
XACC.
good place to start.
Yeah, I really do want to point people to the new AQC documentation page. It's brand new and it's not done. But we will have a developer guide section and we already have a couple of pages up on it. We have 2 pages showing how to make new circuit synthesis strategies and how to make new optimizers. Um, but we need people making new accelerators and new IR transformations for circuit optimization and placement and all this kind of stuff. And so, yeah, I mean, my first piece of advice would be to kind of pull down the papers that I linked at the end and go through the papers and kind of see what the architecture looks like. And then reach out to me and somehow I forget if our Slack is like public or I think it is, but you can join our Slack. That's the best place to talk to the team and the people working on it. And I'm always on it. The team is always on it. So as you come about with ideas and you want to implement this and that, we're always there to talk. So, so yeah.
Sweet. Amir asks, since you mentioned LLVM quite a bit, what are your thoughts about MLIR?
I actually have it written on my whiteboard. So
Prescient question, Amir.
yeah, I'm kind of in this initial research phase with MLIR. I think that I'm a big fan of the LLVM infrastructure. I'm a big fan of Clang. I've, in the last 6 months come across MLIR, and I'm really interested in thinking of ways to connect MLIR generation with Antler, with tools like Antler, like parsers, parser generators. And I think that this actually might be a key um, step toward the integration of what we've got with something like MLIR. And if you do have that, then it's pretty straightforward to lower MLIR to LLVMIR, and also integrate a bunch of different compiler passes at the MLIR level and LLVMIR level. And these are things that we're just now starting to kind of explore. We've got a couple of little examples or prototypes where we're operating on the quantum kernels at the LLVMIR level. So definitely, this is something that I'm interested in as a research, avenue. but we're kind of at the early stages of it.
Awesome. Yeah, someone also asked, is there a public roadmap?
There's no like open public roadmap. I mean, we have our kind of like internal proposal or internal project milestones and things like this, but this is not public. Um, Now that you've mentioned it, this might be a great action item for me to kind of put that together. So
I know we've kind of been looking at doing the same for Mythic, like, you know, kind of making well, I think we have one, but we've now reached the end of it, so we definitely need to kind of
yeah,
extend it, and that can kind
yeah,
of help. You know, we've also opened recently doing community calls. So every Friday when we basically do our stand up at the end of the week to review where we're at on milestones, we actually just do it publicly on Discord now. And it's
that's
been
really
really
cool.
fun to see even some of the people here in chat joining us and then actually contributing new features and stuff that we need. So
Yeah.
yeah, it's very fun to get the community involved.
Yeah, you know, most of our development activity is driven obviously by our funding sources in our projects at the lab. Um, but you know, it'd be interesting to put out like kind of an open source roadmap for XACC and QCOR, and this is something that I'll probably start thinking about soon.
Awesome. Yeah, does any other questions? Lots of people were asking about the links, and I'll get all those added to the Discord, as
I
well
can share my
as
slides with you.
yeah, actually,
Yeah,
yeah, that'd be great too.
yeah,
I can add them to so on the Unitary Fund website we have a page for all the talks, and once we're done today, I'll immediately cut this and upload it to YouTube. So
awesome.
that you can review any parts of it if you miss something. And yeah, we'll have all the links there in the video description and on our Discord afterwards. So yeah, well, thank you again, Alex, for your time.
Yeah,
This has been really really fun. If you can't tell, I'm super stoked about this project,
yeah,
and I really
I,
want to go right now and just see, because one of the kind of projects that got me involved with the Unitary Fund was I got a funded project to do work on QRAM. And one of the things that we were, and actually one of my collaborators was here in chat, Odi Mateo, and we kind of got stuck on the how to do the optimization part. And
yeah.
so like it's like exactly the tool we need to kind of just walk up and then, you know, do optimization passes on it. So
Well, yeah, I thank everybody for your time, and I appreciate the opportunity. I was really looking forward to this talk. I like this community, and you know, we're kind of at the beginning here with quantum software, and it's really great. It's growing, and I'm interested in interacting and collaborating with anybody that's interested in these projects. So, thank you for your time. Thanks, Sarah.
bye everybody.
Bye.